Welcome back to the ChemDoctor, and this video is going to focus on a laboratory experiment that involves determining the molarity and or the percent mass of an unknown acid by carrying out a titration using a strong base for which the concentration is known. Now, I'm going to basically kill two birds with one stone in this video because what we're going to do is learn how to determine the molarity of an unknown acid, and then we're also going to see how the titration is used to do the percent mass of the same acid in a given solution, rather than producing two videos that involve essentially the same exact titration. Now, for those of you that are rusty, remember that a titration is nothing more than the incremental addition of one reactant into another reactant until the reaction between the two reactants is completed. If we know the concentration of one of the two reactants, then we can know precisely how much of the other reactant reacted with that component. So in this case, we have a known concentration of sodium hydroxide. It's 0.043 molar NaOH. And remember, capital M stands for molarity, where molarity is equal to the moles of solute divided by liters of total solution. So our NaOH concentration is 0.043 molar. And we have that established in the burette, which I'm showing schematically over here on the left side of the screen. So remember, your burette is a graduated cylinder with a valve at the bottom of it, which is called a stopcock. All right, and usually in a teaching lab, the burettes are going to hold a maximum of 50 milliliters. So we can control how much solution that we let out of the burette by manipulating the valve. And at the end of the experiment, therefore, we can know precisely how many milliliters of the NaOH solution were utilized to get to the equivalence point. All right, and I want to remind the viewers what equivalence means. All right, so the equivalence point, this is the point where two reactants have completely reacted with one another. Completely reacted with one another. All right, and this is the part that's crucial, in equal molar amounts. All right, equal molar amounts. Now, what does this bit about equal molar mean? So if we look at our neutralization reaction here, our balanced neutralization equation, you can see that the sodium hydroxide and the acid, which we're calling HA, is just a generic term for an acid. The H represents the proton, all right, and the A just represents whatever the rest of the molecule is. And the acid in this case has a molar mass which is equal to 60 grams per mole. And for those of you that are in the know, you realize that we're dealing here with acetic acid. I'll just put that in here. But truthfully, in your laboratory, no matter where it is, the professor, the teacher, they could substitute any acid into this equation that they want. They may have to rebalance the equation, but in this case, the equation we're dealing with is all one-to-one. Remember, a neutralization is defined by the fact that we have a base reacting with an acid that produces as products water and a salt. So this is a neutralization reaction. And when I say equal molar, or at the point where we reach equivalence, what that means is we have provided an exact one-to-one ratio of sodium hydroxide and the acid together. And at that point, the acid that was added into the reaction has now completely reacted. All right, so that's what I mean by Equivalence point, it's the place where all of the acid is reacted. We've added an equal molar amount of NaOH. And where do we find the acid? All right, the acid in this case is in the collection flask, which is shown here in the schematic. This is an Erlenmeyer flask, or in my classes, I tend to just call it the collection flask, just because I find that I think the students get it easier that way. But this is an Erlenmeyer flask, and in the Erlenmeyer flask, we have 20 mils of distilled water, which the students will eyeball in there. We don't. You need to recognize that the presence of water here has no bearing on the chemical reaction between the base and the acid. But I think it's best to have about 20 mils of water in the collection flask. This volume can be estimated. It doesn't need to be measured with a graduated cylinder. The most important aspect of this for this video is that we're going to use exactly 1 milliliter of an unknown acid. So the students are going to use an analytical pipetter to pipette or to obtain 1 milliliter of an acid that is given to them that will be X molarity. So in other words, they're not going to know the concentration of this acid. This 1 milliliter of acid will be added to the collection flask very carefully, so that in essence it's an analytical transfer. And what that means is that the volume is measured carefully, it's transferred without any loss of material, and then to the collection flask we're going to add 4 to 5 drops of the indicator phenolphthalein. Now, an indicator is a molecule, it's an independent molecule in regard to this reaction that changes colors under different circumstances. All right, now, if this is a really basic chemistry class that you're taking in a really basic lab, the teacher may not tell you exactly why the indicator is changing color. And truthfully, it doesn't really matter if you're in the lower level class. You just need to understand that this molecule will change color at a designated place, and that is what's going to tell you where the end of the reaction is. Now, if you're in a more advanced class, then you should understand that this indicator dye is going to change color at a prescribed pH. And specifically for phenolphthalein, the color change is from clear to pink, as indicated underneath my schematic here. And that's going to happen at about a pH equal to 8.8. Now, for the unknown acid that we're using here, just to finish this quickly for the advanced classes, at the equivalence point for this reaction, the pH is going to be determined by the NaA. So the pH of the equivalence point here is going to be about 8.72 approximately. This is an approximate pH. The point being, you can see that the pH of the indicator and the pH of the equivalence point have a high degree of overlap. So we can use this color change to tell us when this reaction is over. All right. Remember, the main thing to see here, in terms of the purpose of this video, is to understand that when we generate the pink color, that is where we know that the reaction is over, and the stopcock needs to be shut down, and then the volume dispensed measured. So moving on now, let's say that we go ahead and we titrate this. So we add sodium hydroxide to our unknown solution that contains a 1 milliliter sample of a carefully pipetted unknown acid. And we go ahead and we do the titration, and we hit our end point. We come to that pink point after dispensing 18.2 milliliters of the sodium hydroxide solution. All right, so how do we figure out the molarity of the unknown acid, and how do we go to the next step and figure out the percent mass of acid in the 1 milliliter of sample? All right, so the first thing we're going to do is we're going to take our 18.2 mLs, and we need to change this value into liters. We have to change it into liters because by definition, molarity is in units of moles per liter. So for those of you that might be rusty, this is how that's done. 1 liter is equal to 1,000 mils. So we're going to divide the 18.2 mLs by 1,000. We get 0.0182 liters. Now, to find the moles of the base reacted, we simply multiply the volume in liters times the moles of the base. The moles of the NaOH per liter. So all I've done here is expand the units of molarity. All right, and you can see that this volume is over 1. So my liters nicely cancel out. And what I've solved for are the moles of the base. So it's going to be 7.826 times 10 to the minus 4th, and that's moles NaOH. Now, you need to go back to the balanced equation and recognize that the coefficients for this reaction are 1 to 1. So that means we've actually, I'm going to move this down here, we've actually already found the moles of the acid. I'll go ahead and carry this out longhand just to make sure that you understand. So here's my moles of base. Now we're going to multiply by the ratio from the balanced equation. So for every mole of HA, there's 1 mole of NaOH. All right, and I'll cancel the NaOHs, and so this value is in fact also the moles of the acid. All right, also moles of HA. Now, lucky for us, most of these kinds of neutralizations that are done in the laboratory are usually 1 to 1. Not all the time, but most of the time, which makes the calculations pretty easy. Now, what you'll notice here is that we're only 1 step away from getting the molarity of this acid, because the original volume that was measured for the unknown acid was 1 milliliter. So we're going to take the moles of our acid and we're going to divide by the 1 milliliter converted to liters. All right, and what we get for the molarity of our acid is about 0.7826 molar. And I'm not really being careful. I'm certainly not being careful with significant figures here. My main concern is teaching you how this is done. All right. So that's we've knocked down our first objective. Now the second one is to find the percent mass of the unknown acid. All right, and we need some additional information here in order to do that. Remember that the original volume of the acid is 1 milliliter that's carefully measured out. Now, for the percent mass, what we're really asking there is in this 1 milliliter of HA, 1 milliliter of acid, this is not pure acid. This is actually, to be really clear about it, this is acid that's been dissolved in water. It's a mixture, all right? And within that mixture, the acid represents a certain fraction of the total mass. So in order to figure out this part, we need to know the mass of 1 milliliter. Now, your teacher, it may have different ways they're going to ask you to figure out the mass of this. And depending on the sophistication of the laboratory, you may do it one way or the other. In my laboratory, based on the stuff that we have in there, I literally have the students carefully do an analytical pipette of 1 milliliter into a paper cup on a scale to figure out the mass of the 1 ml. So let's say with that background that they find out on the analytical scale that 1 milliliter is 0.9653 grams. Okay, so now we're almost ready to figure out our percent mass, and the formula for that is going to be percent mass is going to be equal to the grams of HA determined by titration, all right, divided by the grams of the total solution. So I'll just write that number in here, and then times 100. And to emphasize this fact, I'll put an arrow here and remind you that this is from the titration. From the titration. All right, so let's go back to our moles of HA, which are right here. All right, and I'll circle this in blue. We're going to pull it back out of that molarity. And we're going to multiply by 60 grams per mole because that's the molar mass of our unknown acid. All right, and what I get is 0.046956 grams. That's the amount of acid. That's the mass of acid that is in the original 1 ml sample. So now I can come here and calculate my percent mass. It's going to be 0.046956 grams, and I'm dividing that by 0.9653. That's the mass of the 1 milliliter mixture. This is the mass of the acid by titration. All right, and this is multiplied by 100. And what we get is that the percent mass of acid in the original 1 ml sample is about 4.9%. And this is approximately the percent found for off-the-shelf vinegar, which is in fact the experiment I'm modeling here is to find the percent mass of store-bought vinegar. All right, and with that I'm going to go ahead and finish the video.